Hi, everybody. Welcome. I want to kind of dive right into this session because we have an awful lot of material to cover, and I'm hoping we're going to get it in under the wire here. So I'm just going to dive right in. My name is Tom Diepenbrock. We're going to talk about geospatial features in MarkLogic 9 and the geospatial indexes that we have in MarkLogic. I've been with MarkLogic since 2011. I am with the consulting department and do a lot of work with different customers building different kinds of geospatial applications. And is that better? Can you guys hear okay? Okay. So I have built just a lot of applications, many of them geospatial in nature. We also have Jake Fowler from engineering. Jake, do you want to introduce yourself?
Yeah, sure. Hello, I'm Jake Fowler. I'm a senior engineer on the software development team for the server, and I'm the lead engineer for Geospatial in MarkLogic 9.
So we got the guy who knows everything over here. So I'm going to give you our agenda in story form. I don't know about you guys, but when I first started working with geospatial information, my first project was like this, and I think a lot of people start out this way, so this isn't necessarily about me. This is about a lot of you guys who may have a common experience. We start out looking like this guy. We're confident, we're excited. This is a new thing for us. Maybe we know what a latitude and longitude is. That was kind of the extent of my experience way back when. And I was like, wow, this is going to be really cool. And I started diving into the documentation of the thing that I was working on, and I started looking like this guy, because there was just so much to get into beyond that initial latitude and longitude. I'm timing myself here. So I said, maybe some sample data will help. And a lot of people do this. Okay, I looked at the documentation. It's really complicated. Maybe looking at the data will help. And we start looking like this. Our desks look like this. I'm dating myself a little bit, but when I asked for sample data, a guy showed up with a cart, and literally my desk looked like that when he ran away. I'm like, wait a minute, no, here you go. And then before long, we start looking like this guy. So we want to skip all of that, and today what we're going to do is help you guys kind of short-circuit that little scenario, and we want you to build applications that look like this while you are looking like this guy, and jump over that intervening step. So in a little bit more detail, we're going to go through a little vocabulary, so we're all talking about the same words, and the words all mean the same thing to us. We're going to go through the geospatial features in MarkLogic 9. We're going to have a special focus, actually, geospatial features in MarkLogic. We're going to have a special focus on some of the new things in MarkLogic 9. We're going to talk about how to build applications with them, and we are going to deep dive under the hood into the implementation, actually, in the indexes of this stuff. Quick vocabulary lesson, very quickly. We're going to talk about latitude and longitude. Everybody kind of, hopefully knows what that is, but a little bit of detail on that. We're going to talk about what WGS84 means, because that is actually very relevant to what we're going to be doing. What geodesic arcs are. You may have also heard of those as a great circle. And finally, there's this word, which is a very MarkLogic specific thing called regions. And what does that mean, and what does it have to do with all of these other words? So anybody not know what a latitude and longitude is? I figure everybody does, right? It's coordinate on the Earth's surface, right? Degrees latitude, north of the equator, longitude, east or west of the prime meridian. Sometimes you will see these. Usually it comes latitude first, longitude second, but sometimes you'll see these in XY pairs. And in that case, it is actually longitude first, latitude second. And the only reason I bring this up is because I can't tell you how many times I have gone on an engagement and people are going, why are these points that I expect to be in the Middle East showing up over here by the UK? And it's because they flipped their XY versus latitude and longitude. So I bring them up every presentation I do. Coordinate systems. We implement 3 different coordinate systems in MarkLogic. WGS84, the raw Cartesian coordinate system, and a new one, which is European specific, called ETRS89. We're going to focus today on WGS84 because this is the most frequently used one, at least in our customer base. And the idea behind WGS84 is it hammers home the idea that the Earth is not round. The Earth actually bulges at the equator slightly. And that is what WGS84 attempts to capture as close as we can, is that bulge that happens at the equator. So why is that important? If I asked you to draw me the shortest path between Los Angeles and Paris, most people would draw this line that goes right across here, but that actually is not the case when you're talking about an ellipsoid like WGS84 models. The shortest shortest distance between 2 points on an ellipsoid is actually a geodesic arc, which we've drawn here. Kind of looks weird to go up into Canada and past the tip of Greenland to get to France, but that is actually the shortest distance. Special kind of geodesic arc is actually a great circle. A great circle is a geodesic arc over a sphere. A geodesic arc over an ellipsoid is just a geodesic arc. Why is that important? This is where that word regions comes in. Regions is a MarkLogic specific term that we kind of throw around, and it's an abstract term that means any geospatial figure that we index. So points, this thing isn't going, lines, there we go, boxes, circles, polygons, complex polygons, and multi-geometries are all implemented in WGS84 such that the thing between vertices, for example, on a polygon is not actually a straight line, it is a geodesic arc. So we model that on the Earth's surface, so when we search and when we try to do other operations geospatially, we are actually doing those in a correct form in WGS84. Okay, so vocabulary lesson is over. Let's talk about where we get our geospatial data. We get it from lots of different places. Sometimes we get raw data just from surveying or people walking around capturing points on a GPS. We have actually great data for Fairfax County, back where I come from in Virginia, where a guy actually, one of the things we have is a golf course. And the guy captured the data by walking around the outside of the fairways with a GPS, capturing 1 point about every meter. It's ridiculously detailed data. We can also get it from social media. Every time you tweet using your phone, unless you turn it off, your phone is embedding the latitude and longitude of the point where you are before it posts it to Twitter. Cameras also have GPS. They do the same thing, embedding that into the metadata of your pictures. Language, in my opinion, is where the coolest kind of geospatial data comes from. If I were to say something like, I'm taking the dog for a walk down past the White House, that means something entirely different from, I'm going to take the dog for a walk down past the White House. Right? The second one, obviously, we're talking about a place in Washington, D.C. The other one, we're talking about a place down the street from my house. This is especially important because, in a real operational sense, there are many places where there is no address system. So you can't say, take me to 123 Main Street because the buildings have no numbers and the streets have no names. So how do you find out geospatial information in those things? And the way you do it is through language. And actually, in this case, you might use entity extraction software or even crowdsourcing to know that, hey, this is where Mr. Jones' house is. No street name, no house number, but we know where it is because we have analyzed the language to find that. So what can we do with that? I'm going to give you a quick demo of an application that we have built that kind of illustrates some of that. There we go. So this is just an application that we've built. There's lots of data in this, but since we're in Chicago, I'm going to search for dams, the things that hold back water. So quick search. And what we're going to get back are actually text-based results. So, hey, that's great. I'm just going to look at this first one. And as I go through the attributes of this thing, I'm going to go down and I see a thing that says geometry. I'm going to click on that. And I can see that down here, you can see this little place mark over here. That is the geometry. So we can just visualize these things in a onesie-twosie kind of way. We can also look at these in the aggregate. So what we're going to look at here is a heat map. And a heat map shows us sort of the distribution of our geospatial information for the whole search across the map. Now this thing is showing us that we have a whole bunch of results here in where you would expect. In Illinois, there's actually an outlier way over here in Alaska. I don't know why, but this bubble user interface or a cluster user interface helps us see that sort of thing. We can double click on these clusters. It zooms us in. And of course, we want to be able to search. So I'm going to do kind of an interesting search here where I'm going to follow the track of this little river, mostly as close as I can. That's a little bit off there, but that's okay. And then I'm going to do what's called buffering this thing. Make this a little bit bigger. Save that, whoops, and hit apply. And so what that did is now it has scoped my result set down to only those things that fall within that search polygon. So searching, the aggregate, analysis, and, oops, I just pulled up the wrong thing, and that bubble user interface, which is a super convenient way of looking at your data. So how does this start out? That particular data, this is actually the data set that generated the thing we just looked at. It came to me in spreadsheet form, and I get a lot of data that comes to me in spreadsheet form. I don't know why, but it seems to be the coin of the realm. So we usually start off with raw data that looks something like this. We want to get to something that looks like this. So we're going to look at our functionality. I just showed you. We're going to go through that, the search, the different kind of searches, heat maps, the cluster user interfaces. And so this is kind of a little diagram of that application we just looked at. We have data over here on the left. Maybe we have some point data. We have some polygon data, mixed text. Coming in, we're indexing it, MarkLogic, and the functionality over here on the right, search, heat mapping, and the cluster user interface. So where do you start? I take a look at this data. Frequently, you have to do some conversions. This may be coming in the form of like an Esri shapefile or something like that, and you have to convert that to something that we can index, maybe GeoJSON, some other more friendly form that we can bring into the database. You may have to do some transformations at ingest time, and I'll talk about that in a second. This is also a great time to look at your document structure. Do we want to do that envelope pattern, which is super useful for this, where you can leave your original content untouched, but have some metadata fields that will drive different indexing capabilities. So just an aside, why do we transform at ingest? Because people, especially when they give you spreadsheets, they come up with the weirdest ways to express a latitude and longitude. You will see all of these and more. I've seen stuff like this. And you have to somehow get that into decimal degrees. So get used to transforming some of this data at ingest time. And to do that, I'm not going to go through all of these, obviously, but this is your toolkit for transforming data at ingest time. I put links to the documentation. Oh, no, I'm sorry, this slide doesn't have it, but look at this geo package. There's all of these functions and tons more that will help you transform things at ingest time or do analysis afterwards, too. And this is also when you want to look at your index configuration. What kind of indexes do we want to use? We have two different kinds of indexes in MarkLogic, a point-based index and a region index. Point index, if all you were indexing are points, that would be the index I'd recommend you use. It's in memory, it's super fast. It is also the only index you have available to you if you are using MarkLogic 8 or before. That is also required to drive heat maps in the cluster user interface. MarkLogic 9, we just introduced a region index, which allows us to index and search any of the regions that we support. Now, we used to be able to do this too in MarkLogic 8 and before, but it's a lot harder and requires some custom code. MarkLogic 9, it's all built in out of the box, much easier than it used to be. I'm going to go through the different kinds of indexes that we have right now, starting with the element index. This is a point-based index in memory. Super simple, just says, hey, there is point data at a particular element or JSON property in the database in your documents. An element child index, same kind of thing, except now we're saying something about the structure, about where to find that particular element in the document. The element pair says, hey, we have an element, and underneath the element, we're going to have one element that specifies my latitude, another one that specifies my longitude, and the corresponding structures for JSON, of course. Element attribute index is actually an XML-only index because it takes advantage of this attribute construct that exists in XML, where you have an element name and an attribute for the latitude and an attribute for the longitude. By the way, you don't have to use these names. These are just examples. You'll see in the index configuration that you can have any attribute or element name that you want there. A path index. This is super useful because frequently, GML is a great example of this. You'll have the same element name that sort of serves multiple functions. And in one spot, it will have indexable data, and in another spot, it will have something else completely different. So you want to be able to point the indexer to the right spot in the document to find the indexable data and not the other stuff. And in MarkLogic 9, we have the region path index, same idea as the path index, except not just points. Now you can have any of the regions that we support in MarkLogic that will be indexable in there. So we're still building our application. Maybe our document is starting to look like this. We have our content section where we have whatever the original content was, and we have a metadata section where now I've created a geometry property, and I'm putting in there, in this case, region data, and I've created on that a region path index on /metadata geometry, saying we're going to find content there that you can index. So again, kind of going back to this document, or I'm sorry, this diagram showing where we are. We've had our data, we've converted it, transformed it, put it into MarkLogic, and indexed it. So now we want to talk about how to search it. So I'm going to start with the server-side query APIs. Every index that we have has a corresponding API function to query it. So these are the ones that are XML-based. If you have the word element in your query, in your API name, I'm sorry, that means it will return XML documents to you. If you have the word JSON property, works against the same indexes, but it will return JSON documents to you. The only exceptions to that are the path indexes down here. They will return either one, depending on what they find. So let's talk about, in particular, the new region path index and the query call to query that. You have to understand something about this thing called the dimensionally extended 9-intersection model. Everybody say that real fast, 9 times fast? What that does is it defines different ways that regions can relate to each other. And I put a Wikipedia page up here to give you all the details about that. This is kind of a very quick summary because it's hard to kind of get through all of those things. It's super detailed. Mainly, the differences between these, they're kind of intuitive. But the differences, for example, between contains and covers are the fact that the boundaries of a region are a different thing in the DE9IM from the interiors of a region. So contains and covers mean exactly the same thing, except boundaries count in covers and they don't count in contains, if that makes any sense. Check out that Wikipedia page and it'll become obvious to you. Within and covered by are the opposites of contains and covers. Disjoint is pretty easy. There is no interaction between the two regions. Intersects and overlaps kind of have the other weird thing about the DE9IM, which is dimensionality. So intersects says that two things can intersect regardless of their dimensionality. So a one-dimensional thing can intersect with a two-dimensional thing. That's perfectly fine. Or a zero-dimensional thing, a point can intersect with a two-dimensional thing. Overlap says, they got to be of the same dimension. So only two-dimensional things can overlap with two-dimensional things, one-dimensional things with one-dimensional things, and so forth. So getting back to these query parameters, to query that path region index, you're going to say, hey, query this region index. You give it a predicate, my region index, where the data covers my search region that I'm going to submit as my query parameter. Finally, I want to mention CTS parse. This is for user-entered query strings. It gives you a way for power users to enter a query string that this will parse out and generate those queries on the fly. So we also have the client APIs. REST, Java, and Node all have queries to query those indexes as well. And the documentation links are here. And now we know how to search. Or I've given you at least the references for how to search. Let's go on and talk about heat maps. So heat maps, you want to use a query options node. And there is a good reference for the query options here. If you're used to using the search API or any of the client APIs, you're used to using these options. So to generate a heat map, you're going to add this little heat map parameter over here, which basically defines a grid. So the corners of the grid and then the number of divisions vertically and horizontally that you will use, and it will return to you a box and the number of results that are found within each grid. Be careful of the divisions. So you're generating facets with this. So to give an extreme example, if you set this lat divisions to 1,000 and long divisions to 1,000, you're asking the server to generate 1,000,000 facet values. So that is quite a lot. So make sure you set those divisions to something reasonable for the region that you are searching over. So now here's our Notional App Document. We have our geometry property, but now we need a centroid point, right? So if I have a polygon, I don't want to search over the points in the polygon, I want to search over the centroid. So we have an operation for that called CTS approximate center. I think that was on the previous slide. That will help generate that. So now I'm adding another piece of metadata, and I'm putting an element index on there to drive that heat map. There is also a client API for all of these. So again, REST, Java, Node. Node is a little different than the other two just because it's Node. If you're used to programming in Node and JavaScript, that will look very familiar to you. And if you are not, the more programming in Node and JavaScript that you do, the easier that will become to you. But it is structured a little bit differently from the other ones just because the language is a little bit different. So that covers heat maps. Now we're going to talk about the clusters, or a bubble user interface is the other thing that's called. How these interfaces work usually is that the user interface component does all the zooming out, zooming in, and combining and splitting up the bubbles. So to give it all that data, it needs all of the point data for your search, and it needs it really, really fast. So you want to pull that out using a values call, which just reads that data straight out of the in-memory indexes and shoves it out to the client as fast as it possibly can. Should be super, super fast. You'll use the same options node here. I still have the heat map reference in there, although that isn't necessary for the bubbles. Again, I put that CTS approximate center call in there because you're going to need that for the centroid points. You're going to be feeding those centroid points out. And here's the API client calls for that. So again, REST, Java, they look pretty simple. You're going to use that values call. It will shove those point values out as fast as they can. Node looks a little bit different, but again, it's just a syntactical, structural kind of thing. It is doing exactly the same thing under the hood in MarkLogic. So again, if you're used to programming in Node, that will be very natural to you. And if you're not, you'll get used to it as you do more Node programming. So now we know how to do all of those things. We haven't gone into super detail on that, but we definitely want to get this out to you so you sort of know the different tools that you have available to you. Links to the documentation are in there. And that's going to wrap up the application level pieces. And now I want to hand it over to Jake, who's going to talk about what is going on under the hood with all of this.
All right, thank you very much. So I'm going to talk a little bit about how these indexes actually work under the hood. The overall flow will be first, we'll need a little bit of background on how indexes work in MarkLogic in general. In particular, the two kinds of indexes that are important for the geospatial indexes are the universal index and MarkLogic's range indexes. And then we'll talk a little bit about the point indexes and the new region index that's introduced in MarkLogic 9. So to get started, what happens when you ingest a document into MarkLogic? So let's be specific. Here's an example document with some geospatial data in it, as well as some other data. So what happens when this document comes into MarkLogic? Well, even if you haven't configured any special indexes, MarkLogic's universal index will index certain properties of the document. In particular, it'll index words. So for example, here the words MarkLogic and HQ occur in this document. If you have phrase searches turned on, it'll index phrases, like MarkLogic HQ. If you have trailing wildcard index turned on, it'll insert terms like this into the universal index that'll allow you to search for words that begin with MAR, for example. And additionally, it'll index facts about the structure of the document, such as the fact that there's a building element, a name element, and even parent-child relationships between elements, and many, many more. So even a simple document like this one can result in a lot of terms being added into this universal index. So the universal index that gets built up consists of essentially a list of these terms, together with, for each term, a list of which documents contain that term. So when comes time to search, if I wanted to do something like, tell me all buildings whose name begins with MAR, what the query plan will do is break that into certain individual facts, such as, well, we're looking for buildings that have a name, we're looking for words that begin with MAR, and that'll return a set of results. And we won't necessarily have indexed that particular fact. We didn't put that fact that the building's name begins with MAR into the universal index. But by combining together the facts that we do have, we can limit the scope of the results down to, to the point where any false positives can be filtered out using the filter step. Now, the universal index is great for searching for specific facts, but sometimes we're interested in ranges. So for example, this height element, we may be interested in finding, all buildings whose height is taller than 10 meters. Well, we can't search the universal index for every number that's greater than 10. There's an infinite number of those. So instead, we make use of a range index. So if you configured a range index on that height element, then you would end up with something like this. So this would essentially be a list of documents, but it's sorted by the height. So when this document is ingested, if you had that range index configured, then the document would be inserted in the appropriate place in the list. When it comes time to query, so for example, here's a sample range query, find all buildings whose height is between 8 and 14 meters, this query can be resolved very quickly because all of those documents are together in the index. So we just grab all of those documents and return them as the result. Okay, now moving on to the geospatial part. So this is an example of what a geospatial point search might look like. So here we're returning, say, all points in the state of California. So how does this work? Well, geospatial point indexes are actually a type of range index. So again, we see here we have a sorted list. And this time they're sorted by the latitude and longitude. So first sorted by latitude, and then if in the case of a tie, sorted by longitude. So if you had this point index configured and you ingest this document, the indexer will notice that you have that location element and insert the document in the appropriate place. Now when it comes time to query, so say for example you wanted to do a point in box query. So here's an example of a box. We have a latitude range and a longitude range. So effectively this becomes two ranges. So first we filter out by the latitude range, and all of those documents are together in the index. And then within each latitude band, we can then filter by the longitude range. And so this is how the geospatial point index returns, finds its result is based on these boxes, which consist of two ranges. So here are the results that would be returned from this query. Now, of course, most interesting regions on the Earth are not boxes, but instead can be represented as polygons. So here, for example, we have the city of Chicago. So how does point and polygon queries work? Well, the first step is that we actually approximate the polygon by using boxes. So this is what that would look like. So here we've approximated the city of Chicago by using only boxes. You can see the boxes that we use by calling this geoBoundingBoxes function. Then we query the range index using those boxes for candidate points. So for example, maybe we find these 2 points are within those boxes. But these boxes are only approximation of the original polygon. So we actually have to take each point and compare with the original polygon, and we may have to throw out some results. Like we can see up here, this guy occurs in a hole in the polygon, so it has to be eliminated. Okay, now let's talk a little bit about the new region index that's introduced in MarkLogic 9. So this is an example of what, say, a within query might look like. So we're searching for, in this case, these are zip codes, actually. So zip codes that are within this circle would be the query that would have generated this, this result. So in fact, for region search, we actually have 2 different methods of indexing depending on what coordinate system you use. So for the geographic coordinate systems, which are WGS84, points on the surface of the Earth, we use a technique called geohashes. Now for the raw coordinate system, for the Cartesian coordinate system, we use a technique called R-trees because geohashes don't apply in the Cartesian coordinates. So first, let's talk a little bit about geohashes and the geohash index. So what are geohashes? So here's an example showing a picture of the geohashes of Chicago. Now, I actually will show you a little demo that I have that's powered by the Geohash APIs introduced in MarkLogic 9. So here we have a map, and what I can do on this map, I'll lower the precision. So if I put some points down, we can see that these points lie inside of certain boxes, and these boxes have names. So for example, this point here is in the box 9Q9J2. And notice these nearby boxes will tend to have names that sort of start similarly. Like here we have 9Q9J3, 9Q9J6, and so forth. We can also adjust the precision. So if you want to be more precise, we can specify a longer name, 9Q9J36, and get a smaller box. Or you can specify a shorter name and get a bigger box. So here, all of these are within the box 9Q9. So notice that as we get bigger, the boxes' names have this prefix property. So 9Q9 contains a bunch of boxes whose names begin with 9Q9. Additionally, we can calculate geohashes of regions, not just of points. So for example, if I draw a polygon here on this map, now we see we get not just one geohash, but a set of geohashes. And you'll notice that in the case, well, first of all, notice that we distinguish between the boundary geohashes and the interior geohashes. So the interior ones are entirely contained in the polygon. They're showed in green, and the red ones are the boundary geohashes. Another thing to notice is that here, for example, this one, this 9W, because we contained all of the 9W geohashes, we can shorten that and just store the big box. Quick question. Oh, yes. Yeah, so that's a great question. Well, it turns out that when you draw straight lines on the map, you don't get quite accurate representation of the shortest distance. So you'll recall that if we show the geodesic arcs here, we see the actual path between these 2 points actually arcs northward a little bit higher than the map would lead you to believe. So those are actually boundary geohashes and interior geohashes. Great question. You actually beat me to the punch. I was about to say it, and then you asked. Okay, so as we noticed, we have this prefix property of the geohashes. So smaller boxes are prefixes of bigger boxes that contain them. So if you're interested in geohashes and want to play around with them, we offer a whole bunch of APIs for dealing with geohashes in MarkLogic 9. In particular, the first one here, Geohash encode, is the one that that demo was making use of primarily. So that takes in a polygon or point or other region and outputs the geohashes. Geohash decode is for if you want to know what box does this geohash string represent. And then these other ones do various other useful things with geohashes. So how do geohashes relate to indexing of documents? So here we're back to our example document, only now I've added some more geospatial data to it, in this case the outline of the building. So if you have a region index configured on an XPath, say building/outline, then when you ingest this document, the polygon will be parsed into our binary format, internal binary format, and we'll calculate the geohashes of it. So here we have an example of some geohashes. Then what happens is that each geohash will result in a term in the universal index. So this term in the universal index represents the fact that this document contains a region which has a geohash of 9Q9Z6Y. But we also insert some additional facts, which will come in handy later, which is related to that prefix property that I was talking to earlier. So these are sort of like trailing wildcard terms for geohashes. So these would match any, these would be used to search for example, any geohash that begins with 9. Now what happens at query time? Say we wanted to search for database regions that intersect with a given query region. This is what this query would look like if you were to write it in JavaScript using a CTS geospatial region query. Well, when the first thing that we do with your polygon or other region when you search is we geohash it. So we calculate the geohashes, and then each geohash will give rise to a set of search terms that we're going to query the universal index for. Now, the set of search terms will be different depending on the different operations. So intersects will yield a different set of terms than contains, so forth. So in this case, we were doing an example intersects query. So we're looking for, let's focus again on this 9Q9Z6Y geohash. Well, first of all, if the document contains that exact geohash, that indicates a possible intersection. So we'd want to search for that. But additionally, there are other geohashes that could indicate possible intersections. So for example, a geohash that contains this box. So we want to search for that one as well. And in fact, we want to search for all the prefixes. Now that's still not enough because there could be a smaller geohash contained inside of that. And we want to search for that as well. And that's where those prefix terms come in. So we would be searching for that term. So then each geohash results in this set of search terms, and collectively, all of those search terms are submitted to the universal index to resolve the query. One important thing to note about this is that just because the geohashes match doesn't mean the regions match. So here in this example, even though these two regions share a common geohash, the regions don't actually intersect. So you can end up with false positives from the geohash index, which have to be resolved using a filter step. So if you're interested in diving more into how this works, you can see these search terms that are generated by using XDMP plan on your region queries. So if you were to run XDMP plan on that query, you would see, first of all, we've geohashed the region and calculated its hashes. And then in the query plan, you'll see that we're searching for various geohash terms based on those hashes we calculated. And one little wrinkle that I didn't talk about earlier is that we do distinguish between the boundary geohashes and the interior geohashes. So that is because some of those DE9IM operations depend on the depend on the boundary, right? The boundaries matter, for example, for covers and contains. Additionally, we can see those prefix searches in the query plan. And furthermore, we can see these terms here, which have prefix in them. These are those terms I was representing earlier with the star. So these are these sort of trailing wildcard style search terms. OK, so that's the geohash index. Moving on, the raw coordinate system makes use of a different indexing technique called an R-tree. So again, the index is configured similarly on an XPath expression, and the region will be parsed when the document is ingested. But for the raw coordinate system, geohashes don't apply. Geohashes have geo in the name, right? They only apply for geographic coordinate systems like WGS84. So for the raw coordinate system, what we do is, first of all, we persist this region in a long-term storage. And secondly, the index part of this, the R-tree, is based around the bounding box of the polygon. So that bounding box will get inserted into the R-tree index. So what does the R-tree index actually do? So the R-tree, so as you're inserting these documents, you'll end up with a whole bunch of bounding boxes of all of your regions in the database. So, so when it comes time to query, so what the R-tree does is it provides a method of aggregating together bounding boxes that are close together. So for example, these bounding boxes, we can clump them together into one big box. Similarly, these guys in the middle, we can clump them together and maybe the guys on the right will be clumped together into a big box. And then maybe we'll clump all of them together into one big box. And this would be the root of the tree, with the little boxes being the leaves. So when it comes time to search, we'll calculate the bounding box of the query region, search the R tree, and then search the R tree to find candidate matches. Then each candidate match gets, so once we have a candidate match, because the bounding boxes indicate a match, then we can actually go and retrieve the region from storage and decide if it matches. So how does the query work for the R tree? So here's our query region in black and our R tree root in blue. So the query sort of goes the opposite way from building the R tree. So we start at the root and say, well, okay, we overlap here, so maybe that indicates a match, so we have to drill down into the tree. Now we can say, okay, well, this guy on the right can't possibly intersect. So we can eliminate it, and we only have to drill down into these two. Then we drill down further, and we say, okay, well, some of the boxes don't match, like this one over here can't possibly be a match, so we can eliminate it. And then we have now our set of candidate matches. And so for each one, we have to retrieve the region from storage and compare it with the query region and see if it matches or not. And in this case, it does match, right? We have an intersection. Okay, so just a quick summary. Some of the new things in MarkLogic 9, geospatial region search, which we've just discussed. One thing that didn't get a mention earlier, but it's actually a really cool feature, double precision. So this is for if you need really precise measurements. Double precision actually offers accuracy down to even sub-millimeter on the Earth. And additionally, there was this ETRS 89 coordinate system for the European region. And we have a lot of cool things in the pipeline coming. So in 9.02, you can expect to see some more operations. More of these DE9IM operations will be supported. We'll be introducing a new secondary index for the geographic coordinate system, which should improve the performance and eliminate the issue of false positives. And additionally, a couple of new functions that will allow you to just directly compare two regions using those DE9IM predicates without configuring a region index. So if you want to dig into some more reading, the documentation, there's a great guide for geospatial search that covers both point and region indexes. And the white paper inside MarkLogic server has a great section on the point indexes. The region index is a little too new to be covered in that, but hopefully it will be in the future. All right, and that's all. Thank you very much. And I would like to open it up for any questions. Yes. Oh, by the way, if you could wait for the microphone, because this is being recorded.
When you were showing the Geohash boxes, you drew them with straight lines, but should those also be drawn with the geodesic lines?
So the boxes actually, the verticals are meridians, right? So those actually show up correctly in that Mercator projection, which was the projection that's used in that demo. For the horizontal lines, actually for boxes, those are not geodesic arcs, those horizontal lines. Those are actually latitude lines, which are not geodesic arcs. So actually those show up correctly as well on the Mercator projection. So the boxes actually were displayed correctly.
So for the longitude lines, I agree they'd be straight, but then wouldn't they be like more polygon instead of a rectangle?
Well, it depends on we're getting into sort of the issue of map projections and how sort of visually representing. Of course, we're representing stuff on the surface of the round Earth on a flat plane. There's always going to be some distortion involved. In this case, for the boxes, actually, that particular projection, the meridians actually show up vertically. All right, any more?
Can you store the results of the intersection operation?
Sorry, say again?
Can you store the results of the intersection operation or overlaps or contains?
Can you store the results of the intersection operation? Well, I mean, you can store the results of any query in a variety of ways. And there's certainly a lot of interesting possibilities there with the results of, say, a region query, persisting those to... yeah, so I think the answer to your question is yes.
So when you do the query, if you intersect polygon A and polygon B, do you get the actual intersection region itself?
Oh, I see, I see. So the answer, so right now, no, we only tell you if the regions intersect or not. We don't tell you the actual polygon or region of the intersection. All right. Any more questions? Oh, yes.
Wait for
Oh, microphone, 1 sec.
Hi. One of the challenges we're having right now with the geospatial is we have a business requirement where we're returning about, say, 5,000 results. And on the geospatial side, it's not necessarily a problem with getting the results back. Normally, for performance reasons, we do like lazy loads, and we'll do like, literally 25 a result on a page and go through because it's expensive getting the documents. This requirement right now is, in addition to the Latin long, we each also need to be showing information specific to the item, such as a title and other things. A dollar valuation, other items, and we're being challenged with doing this efficiently.
I see.
We tried using, I think it's the CTS tuples, if I'm not mistaken, but then we're needing to create additional indexes and field indexes, and I kind of feel like there's got to be a better way. I don't know if it's a problem you guys have dealt with before.
What you may want to look at is actually faceting. It sounds to me like that's more of a faceting or a bucketing use case.
Well, no, the problem is this, is that since we want to use like Google Maps or another facility, is they need to, for them to do the, drill down and everything, they're looking for more results. I mean, one of the things we're toying with is literally changing the metaphor on this thing a little bit. In other words, like starting out by doing facets, because we have them, but then at some point getting to the actual, down to the geospatial, but ideally, they would like to actually have us pass all the Latin longs, which we can do efficiently. It's really works very nicely, but it's when we try to throw the additional data on there that we're having.
I see.
problems.
Yeah, so you may...
Yeah, multiple labels. It could be 5 or 6 items. So things that we already have range indexes on, the CTS tuples is working nicely. Where we don't have range indexes, we're thinking we maybe have to create fields, and then we have problems if any of the items in the fields are null, nothing comes back. So it's, this one, just wondering if it's a problem that I figure maybe people have already solved.
That may be something we want to maybe talk about offline, but I think there are definitely a couple techniques that you might want to use when you have to, the general question is how do we pull out lots and lots of data from the database as fast as we can in order to display to some other component.
The geospatial works nicely, and then stuff along.
Right, so we'll want to talk about maybe some different techniques to do that. There are definitely some things you can do to speed that up.
Okay, I think we're up against our time limit here, so I want to just thank you all very much and enjoy the rest of the conference.
And if you